A very good morning, class. Uh, as we have seen so many case studies regarding fatigue, brittle, and ductile, here there is another case study which is going to study about creep or creep failure. Okay, we all know creep failure mostly happens at the elevated temperature or at constant loading. Okay, here we are going to see a case study of a creep failure of boiler reheater tubes in a power plant. Okay, let's go inside. Before going to the actual part, we are going to know what is the background of the creep failure. Okay, as that the boiler was commissioned for 24 years ago, and it's an operation for 150,000 hours. Okay, and the tube material is SA192. It's a medium carbon steel. It's a seamless tube. The outer diameter, normal thickness, and work pressure is given. The working pressure is under 345 psi. That is 345 pounds per square inch. Okay. Okay. This is the boiler tube. Before it's cleaning, it's look like this, and after it has been cut into the pieces. It is after cleaning, you can see like this. We are going to have a clean microstructure or a clean microstructural view over it. Okay. Taking the microstructure part, you can see this is the cross section of the pipe 3. We are going to see 1 2 3 4 5 pipes. Okay, this is the cross section of the pipe 3. The first is a simple or normal without a standard pipes. Okay, coming to the pipe 3, you can see ferritic periodic structure. This is a ferritic periodic structure where you can see there's a carbide which is acclimated to the grain boundaries. Okay, see here, this is the carbides which is acclimated near the grain boundaries. As this carbide act as both a volatile material, but and also as a volatile material and also a useful material. We have to know what has actually happened here for this in this case study. Okay, taking it, this is a ferritic periodic structure where the carpets has been accumulated in the grain boundaries. Okay, taking to the next part, taking to the taking the cross section of pipe number 3, that's the fire side. This is the fire side. You can, it's already seen, it's carpets are precipitated in the ferrite matrix and it's precipitated at the grain boundaries. This is at the ferrite matrix and also in the grain boundaries. Okay, taking it to the in a better way, while we are seeing this in the microstructure, you can see this is a periodic structure and a huge dispersion of carbides. This black colors are the huge carbide precipitation which is accumulated in the grain boundaries. These carbides not only helps in increasing the strength or hardness. At the same time, it has some disadvantages, like it acts as a stress concentrator area. Once the stress concentration happens in the metal, you can see this stress concentration. Once this happens in the metal, you can see or you can find metal or a dispersion, or this stress concentrator will act as a this stress concentrator will act as a thing which is called as the stress concentrator thing, which will act as a initiation site, a starting site for the crack to occur. Okay. Here from the discussion, you can see the structure is a ferritic periodic structure as it is seen here. This is a ferritic periodic structure. The dispersion of carbides in the ferrite matrix, as it is seen here, the dispersion of carbides in the ferrite matrix. Okay, dispersion of carbides in the ferrite matrix. Sorry. Okay, and the accumulation of carbides in the grain boundaries. See, this is the accumulation of carbides in the grain boundaries. So coming into the structure, the presence of voids in some cases. Okay, the presence of voids may be this black color. Okay, taking here the carbide which is present in the microstructure has been showing that these carbides and the voids that is present in the grain boundaries will act as a stress concentrator. This stress concentration factor, with this stress concentration factor may lead, or it will be leading to the formation, or it may be the thing is called taking this as a step towards the towards the stress concentration area. Okay, the stress concentration will act as a initiation point for the cracking. Okay, once the cracking starts, this cracking on loading, this is also high temperature application. On loading with this high temperature, the creep starts. The creep starts to form. As we have already seen the creep curve to some extent from instantaneous point to some extent, this creep failure will fight against will fight against, or we can say the crack propagation can be stopped up to some primary up to the point where the primary cracking starts or the primary creep starts. Taking to the primary creep into the concern, you can see this primary creep will move on with time, okay, at a slower manner. But due to the high temperature or that constant loading, you can see the secondary creep forms. It moves at a minimum rate there also. But when we goes on, or when we move go on after or goes on applying heat, so the material or the concerned material will be at a highly loaded condition, or at as a highly thermally it's loaded in a thermal condition, or we can say it's thermally loaded. And also we can say moreover this thermally loaded condition, then we are going to also add some constant loading, like it's a heat exchanger tube, so we can have some pressure which is constantly applying on it, okay, with and also a temperature. This pressure acting as a constant loading, so making the combination of these two will forms the creep. Okay, combination with these two will form the creep. As goes on doing this, the third tertiary creep goes to occur. Once the tertiary creeps occur, it will move more rapidly, more vigorously, and the failures is happening. Okay, coming to the conclusion part, as the result of metallographic, there is the involvement of creep type behavior in the reheated tubes of the boiler unit pipe of 3 and 4. Okay, the recommendation is that as the reheated tubes of boiler 3 and 4 appears a deterioration due to the influence of crab behavior. So it is better to be have the material like low alloy steel as a better choice for operating boilers above 5 degrees Celsius. As we here you are using medium carbon steel, this medium carbon steel upon heating converts this carbon to the carbide form. So these carbide forms will help us or will act as a crack initiation point. Okay, will act as a crack initiation point. Coming to, so this crack initiation point will always lead to this act as a stress concentrator. The stress concentrator will lead to the crack, and the crack propagates, and finally failures occur. Okay, so the better choice is that to use low alloy steels at the temperature above 5 degrees Celsius for any applications, particularly boilers. Okay, okay, that's all for today. Okay, think about it, keep it in mind. What is low carbon steels, low alloy steels can be used for high temperature. Second, on constant loading and high temperature, the most obtained failure or most seen failure is a creep failure. Okay, thank you class, that's all for today.